Okay, so recall the notation e to the I t population u naught. We define this as e minus x squared over 4 it 4 pi it n over 2 convolution u naught, and this was equal to e to the 4 pi squared it psi squared u naught transform, all anti-transform, and this we obtain this definition by obtaining the solution of the linear Schrödinger equation. Okay, so now some properties or propositions of this function. Let's say that okay, well, first for all t real number, that e to the it population, it goes from L2 Rn to L2 Rn is an isometry, which implies that the norm 2 of EIT population F is equal to norm 2 of F. Then the second is that if we have a EIT population and EIT prime operation all applied, then we have that this is equal to ET plus T prime operation. This is what we are expecting if we sum the exponents, and we can say that E minus IT Laplacian this is equal to E to the IT Laplacian, but all to the minus 1, and we can say that this is, well, the same operator conjugate star. Okay, and the third one is that EI0 inflation, what we are expecting is that this is 1. Okay, and the fourth one, if we fix f equal to, then the function of phi of f goes from R to 2 for n. We define that by phi f t is equal to EIT population applied f. Okay, so it's going to be a continuous function. That is to say that it describes a curve in L2. So generally, if we have a family of operators, for example, tt, infinity, minus infinity, infinity, okay, defined on a Hilbert space H, which satisfies these four properties, then these are called unitary group of operators. Okay, so the theorem has done. The family of operators, well, t from minus infinity t minus infinity to infinity, that are defined on a Hilbert space, H, let's say, is a unitary group of operators if and only if it exists a self-adjoint operator, let's say A, not necessarily bounded, okay, on H, such that TT is equal to EITA. So we have a characterization of the family of operators that are a unitary group of operators, and that can be all written in this way, where A is a self-adjoint operator. Okay, so we have to consider this equality in the following sense. If you consider that DA is the domain of the operator A, which is dense in H, okay, if F is in the A, okay, then we have that the limit t goes to 0 of TTF minus F over T is equal to EAF. Okay. Okay. This means that if F is in the A, okay, then the curve that we define phi ft is differentiable in t equal to 0 and with derivative EAF. Okay, A is called the infinitesimal generator of the unitary group. Okay. Okay, so in the linear Schrödinger equation we have EIT. In this case, what we call A is the Laplacian with dA equal to H2. Okay, so that we have the functions in L2 and the derivative, the first two derivatives are in L2, so one can apply the Laplacian. Okay, so now a lemma. If t is different than 0, 1 over p plus 1 over p prime is equal to 1, and p prime is between 1 is in the interval 1 2 close. Then we have EIT inflation goes from LP prime Rn to LP Rn is continuous, and the norm EIT inflation f p is less than equal than constant c absolute value of t to the minus n over 2 multiplied by 1 over p prime minus 1 over p multiplied by the norm of f p prime. Okay, so we have the bound for the unitary group of operators of this type, inflation. So let's see the proof. Okay, so we know that from the position that EIT inflation going from L2 to L2 is isometry. That is that we have that EIT Laplacian F2 is equal to norm F2. Okay, Okay, and also we will have that EAT population f norm infinity is going to be equal, okay, let's say constant Cn EI, well, the variable, we're going to do the convolution 4 pi it is to be to the n because it was n over 2, convolution f infinity, and we have to apply Young's inequality so we can separe this EI, the variable squared for t 4 pi I t n infinity, and we will have on the other side f norm 1, and this will be less than equal then now we can bound this by c plus the value of t minus n over 2 multiplied by norm 1 of f. Okay, now so we can use the Aristotelian theorem now, because we know that we have an operator bounded from L to L2 and from L infinity L1 to L infinity, we can say. Okay, so we know that it's going to be bounded from LP theta to Q theta. Okay, and we had that 1 p theta was equal to 1 minus theta would be naught plus theta over p1, and we will have the same for q's, and the thetas were between 0 and 1. Okay, so in this case we will have that 1 over p theta is going to be equal to let's say in this case we will have 2 and 1. Okay, so we will have 1 minus theta over 1 plus theta of 2. Okay, and we will have that 1 over q theta is going to be 1 minus theta over infinity plus theta over 2. So here we have that 1 over q theta is going to be theta over 2, and in this case we will have that 1 over theta is equal to 1 p theta minus theta over 2. Okay, so we will have that ET Laplacian is going to go from LP prime to LP of Rn always. 1 over p plus 1 over p prime equals to 1, and that we can bound now by p is going to be less than equal than, well, the bound that we had 1 minus theta, because this is what Rizzarin tell us. Of the norm of f p prime, this is going to be equal to ct minus n over 2 1 over p prime minus 1 of p norm f p prime, where, okay, now changing the notation that we did in Rizzarin, we had that 1 over p theta over 2, and 1 minus theta is 1 minus 2 over p, 1 p prime minus 1 p. Okay, so this is what we wanted to see. Okay.